In this video, we're going to be talking about phase changes and how they are related to the strengths of intermolecular forces. You are going to need a notebook, you're going to need something to write with, and once you have both of those ready, let's go. Okay, so what I'm going to get into in this lecture is commonly called kinetic molecular theory. The idea behind kinetic molecular theory is that the state, or what we call phase, of a substance can be determined by comparing the amounts of each different type of energy that it has. So you can compare the kinetic energy of a substance. Kinetic energy, remember, is temperature. And the potential energy of a substance, which in this case is represented by the strengths of their intermolecular forces. For molecules that are in a gas state, gas molecules have very high kinetic energy. They're at high temperature. That means that they are moving about very quickly and rapidly. But gas particles have no intermolecular attractions between them, which means there's nothing to keep them held together. They are free to spread apart as much as they need to fill the volume of the container. Liquids have kind of a moderate kinetic energy, so they're warmer, they have a higher temperature than solids, but nowhere near as high as a gas is going to be. So they do move, right? So the fact that they can move means that liquids are allowed to flow. But in a liquid, the intermolecular forces are strong enough to keep the molecules somewhat close to each other, right? So you're not going to have water molecules just randomly flying off, detaching themselves from other water molecules in large amounts. Right, so again, the idea is they're held together tightly. They take the shape of their container, but they have a defined volume, and liquids are able to flow. Now, when you talk about a solid, solids have very low kinetic energies because they're kept at fairly low temperatures. And also because the particles in a solid are in fixed, rigid positions, they have extremely strong intermolecular forces that keep them attracted in that state. Okay, so that's how the three different states work. Now, what I'm going to show you in the next couple of slides is an example of what's called a heating curve. And we're going to go over the heating curve in each of its individual stages. Okay, so this is a heating curve. The way that a heating curve works is you measure the temperature of a substance as a function of how much heat you've added. You can either do that in the amount of heat in joules or calories, or you can do it by time if you have a heat source that's fairly consistent. So what we start off with is we generally start off at a very low temperature with the pure solid. Right? So at the beginning of the graph, the far left, we have a pure solid. And as we start heating up that solid, what happens is that the solid will start heating up. Right? Once it gets to its melting point, the solid will start melting. Melting, remember, means to go from being a solid into being a liquid. Now, the interesting thing to notice here is notice how for the melting line it's horizontal. So that means that when you melt a solid, its temperature doesn't actually change. It stays the same. Right? Then, after all the solid is melted, you start heating the liquid. The liquid will continue to rise in temperature, and it's a pure liquid at this point, up until it reaches the boiling point. And once it reaches the boiling point, you'll start vaporizing the liquid, which is the process of turning it from a liquid into a gas. Just like melting, while you're vaporizing, the temperature doesn't change. After you have vaporized all the liquid and you're left with nothing but gas, what's going to happen is that any remaining heat that you add is going to go to raise the temperature of the gas particles. So this is a heating curve. It's a diagram that comes in 5 stages. What we're going to do in the next 2 slides is we're going to break these up into 2 sets of steps. One step is about kinetic energy. The other step is about potential energy. So here you notice I pulled out a little bit. I pulled out the melting and vaporizing portions of this graph because what I want to focus on are stages 1, 3, and 5. 1, 3, and 5 involve heating singular states of matter, right? So heating a solid, heating a liquid, heating a gas. Whenever you have only one state of matter present, any energy that you add will cause the temperature of that substance to rise until it gets to the boiling point or the melting point, whichever transition for the state that you're working with. The reason why this happens is that in order for a molecule to break its intermolecular forces or weaken them, it first has to be going fast enough to be able to separate. Right? So if I have a liquid and I want to turn my liquid into a gas by vaporizing it, my liquid particles have to be moving fast enough so that they can actually escape the liquid surface. That's why we have to heat liquids up to their boiling point. Okay, so when you have a pure state, all of the energy goes to affecting the kinetic energy, which is the temperature of the substance, until you reach the point of the phase transition. Now, if we look at the phase changes, right, so melting and vaporizing, again, as we said earlier, these lines are flat. The temperature remains constant. The reason why is because once the molecules have reached enough kinetic energy that they can start splitting apart from each other, all of the energy that you add goes to either weakening in the case of melting or breaking entirely in the case of vaporization, whatever intermolecular forces were present in the sample. Right? And one thing to keep in mind is that if you see the diagram right here, the line for vaporizing is longer than the line for melting. The reason for this is because when you melt the substance, you just weaken its intermolecular forces enough to let it move around a little bit and flow. But when you vaporize, you completely get rid of all of its intermolecular forces, and getting rid of them completely takes a lot more energy than weakening, which is why it takes longer on that graph. Alright, so those are phase changes, solids, liquids, gases. Then we talk about melting, vaporizing. Now you can do this for the reverse process and you get freezing and condensation. And in fact, in your lab, you are going to do a quote-unquote cooling curve because we're going to take the graph as the substance is cooling down. Right, but keep in mind, whichever type of energy you're affecting will tell you what happens to the graph. That's it for phase changes. I will see you in the next video where we talk about boiling, evaporation, and vaporization.